In the black between worlds, there is no air to hold warmth and no wind to spread it. Sunlight crosses the void like a narrow stream, heating only the surfaces it touches. A spacecraft can face the sun and burn with absorbed light, while another panel, turned into shadow, quietly radiates its heat away into darkness. Even near the sun, most directions are still cold, because space itself does not store heat. It only lets energy travel and then vanish into the deep. If this calm journey into the real physics of cold space is interesting, I helps the video reach more sleepers and science lovers. For more quiet, documentary-style cosmic stories like this, subscribe to the channel and continue into the darkness with steady sound and steady facts. Beyond the reach of any single galaxy, intergalactic space spreads out as a thin, almost empty volume. It holds a few wandering atoms, some stray ions, and a scattering of dust grains, but it does not hold anything like an atmosphere. Distances are vast, and the sources of warmth are far apart. In this region, the word cold does not describe a wind or a touch. It describes what happens when energy has room to thin out, when matter is too sparse to store heat, and when light becomes the main way energy moves. In ordinary experience, warmth lingers because air and water carry it. Molecules collide and share energy. A room stays warm after a heater turns off because billions of particles bump into each other and spread the energy around. Intergalactic space does not offer that kind of sharing. Collisions between particles happen so rarely that many particles travel for long times without meeting anything at all. Without frequent collisions, there is no easy way for a region to settle into a shared temperature the way a gas in a box does. Each particle keeps much of its own story, and the overall space between them stays defined more by radiation than by contact. Even so, intergalactic space is not perfectly dark. It is filled with a faint sea of light that comes from the universe itself. The strongest and most uniform part of that sea is the cosmic microwave background, a glow that remains from an early, hot phase when matter and light are tightly coupled. In that early time, the universe is dense and opaque, and light scatters constantly from free electrons. As expansion continues, the density falls and electrons join with nuclei to form neutral atoms, allowing light to stream freely. That released light does not disappear. It stretches with the expanding universe and shifts to longer wavelengths. This stretching is called redshift, meaning the light's wavelength becomes longer as space expands, lowering the energy carried by each photon. Today, the cosmic microwave background fills intergalactic space almost evenly. It is not felt as brightness by human eyes, because it lies in microwave wavelengths, but it carries energy, and it can be described by a temperature. In physics, a black body is an ideal emitter and absorber of radiation, and its spectrum depends only on temperature. The cosmic microwave background matches a black body spectrum closely, so it is natural to speak of its temperature. That temperature is about 2.7 kelvins. In the broadest reaches of space, this is the nearest thing to a universal thermostat. This background glow sets a baseline because nothing can cool by radiation below the level of the radiation field it faces. A small object drifting in intergalactic space, with no internal heat source, releases energy by emitting infrared and longer wavelength radiation. At the same time, it absorbs energy from the radiation around it. When absorption and emission balance, it reaches an equilibrium temperature. If the only surrounding light is the cosmic microwave background, the object settles near that same temperature. It may be slightly warmer if it also absorbs other faint starlight and galaxy light, and it may be slightly cooler in special circumstances if it reflects strongly at the relevant wavelengths. But the background provides the flaw that is hard to evade. Alongside the cosmic microwave background, there is also a more varied, much weaker glow called the extragalactic background light. This includes the combined light of all stars and galaxies over cosmic history, much of it shifted into infrared after being absorbed and re-radiated by dust. It is uneven because galaxies cluster and voids open up. Yet from the perspective of a single drifting grain of dust, it is still extremely faint, because the light arrives from enormous distances and spreads over huge areas. Its energy density is small compared with the intense radiation near a star, and it contributes only a modest addition to the baseline set by the microwave background. The coldness of intergalactic space is therefore not only a matter of distance from the Sun, it is a consequence of dilution. Energy from stars leaves as radiation and spreads outward. As it travels, the same energy must cover ever larger spheres, so the amount of energy crossing each square meter falls quickly. In empty space, there is no medium to hold that energy in place. Light either passes through or it strikes matter and is absorbed. Where matter is scarce, most light simply continues on, and any heated object re-radiates its energy away into the surrounding darkness. The expansion of the universe deepens this tendency. As space expands, wavelengths stretch, which reduces the energy of each photon. The cosmic microwave background itself cools over time for this reason. In the distant past it is much warmer, and in the far future it will be colder still. Intergalactic space does not maintain a fixed temperature in the way a sealed container does. Its radiation field evolves, slowly losing energy as the universe expands, even while stars and galaxies locally generate new radiation. Cold in this region also depends on what temperature means when matter is thin. For a gas, temperature is linked to the average kinetic energy of particles, meaning how fast they move in random directions. In an extremely dilute plasma, particles can have high speeds and still fail to transfer much heat because there are so few collisions. A single fast particle carries energy, but without frequent encounters it cannot share that energy widely. Meanwhile, the radiation temperature of the background describes the energy distribution of photons. These are different measures. An intergalactic space is dominated by the photon measure because it is the most uniform and persistent component. In the deepest voids, where galaxies are absent and matter is at its lowest density, the background radiation still arrives. It comes from every direction, the echo of earlier times. It does not warm in the way a campfire warms a face, because its intensity is tiny. Yet it prevents perfect freezing, because any object that emits radiation into space emits into a bath that is not zero. The result is a quiet cold, not a cold that bites, but a cold that remains when nothing is close enough to share heat, and when the only steady presence is a faint, ancient glow. Around a galaxy, the bright disk and spiral arms are only the most visible part of a larger structure. Far beyond the stars that outline a familiar shape, a faint halo of gas and dust extends into darkness. The halo is thin enough that it does not glow like a nebula to the naked eye, yet it holds a large share of a galaxy's ordinary matter. In these outskirts, cold and heat coexist in unusual ways, because the region is shaped by gravity, bathed in weak radiation, and built from particles that may travel great distances before meeting another particle. The outskirts are often described as a circumgalactic medium, meaning the gas that surrounds a galaxy outside its main stellar body. It is not a smooth shell, it is clumpy, threaded by filaments, and stirred by past events inside the galaxy. Some of it drifts in from intergalactic space. Some of it is pushed out by supernovae and by activity around central black holes, then slows and mixes with the surrounding halo. This region is not empty, but it is still far more rarefied than any atmosphere. That rarity changes how temperature behaves and how heat is exchanged. In a dense gas, temperature is a shared property because collisions happen constantly. In a halo, collisions are infrequent. Many particles move in long arcs under gravity, and only occasionally pass close enough to exchange energy. Temperature can still be defined, but it becomes a statistical description rather than a tightly shared state. The gas may be called hot because its particles move rapidly, yet it can fail to warm a nearby object efficiently because there are too few particles to deliver that energy through contact. Much of the circumgalactic medium around a large galaxy is hot in the sense of particle motion. Gravity draws gas inward, and as it falls, it speeds up. When streams of gas collide or slow in shocks, some of their bulk motion turns into random motion. A shock is a sharp change in pressure and density that converts ordered motion into heat. In halos of massive galaxies, the resulting gas can reach temperatures of millions of kelvins. In smaller galaxies, halo gas can be cooler, and in many halos there are also pockets of much colder material, sheltered within denser clumps. The coldness of space in this region is still set mostly by radiation rather than by contact. A dust grain or a spacecraft drifting through the halo sees a sky that is not truly dark. The galaxy itself fills part of the view with starlight, while distant galaxies add a faint background and the cosmic microwave background remains present. Yet the density of light drops quickly with distance from the bright inner regions. Outside the stellar disk, most directions contain only weak, spread-out radiation. An object that is not in direct starlight radiates its heat away into a vast cold field and receives little in return. Even within a galaxy's halo, the vacuum between particles provides little ability to hold warmth. At the same time, the halo is not a simple freezer. It is exposed to ultraviolet radiation from the galaxy's stars and from more distant sources. Ultraviolet photons can strip electrons from atoms, creating ions, and they can deposit energy into the gas. This heating is uneven and depends on how much shielding exists. Dense clumps protect their interiors because atoms and dust absorb much of the ultraviolet light at their surfaces, leaving the inside less affected. Thin gas remains more exposed and can stay ionized even when its density is low. Cooling competes with heating. Gas cools mainly by emitting radiation when collisions excite atoms and ions, and when electrons slow in the electric fields of ions. In very thin gas, collisions are too rare to produce strong cooling, so the gas can remain hot for long periods even though it sits in a cold radiative bath. In denser regions, cooling is faster, and cold clouds can form and persist as separate phases within the same halo volume. Observations indicate that halos often contain multiple phases at once. Diffuse hot gas can shine faintly in X-rays, while cooler, denser clouds reveal themselves by absorbing specific wavelengths from background sources. This absorption shows where particular ions reside, which in turn reflects temperature and density. The signatures also show that halo material is not mixed like a stirred liquid. It is a turbulent medium where motion, magnetic fields, and pressure differences can keep warmer and cooler regions distinct. The reason the halo can be hot while space feels cold comes back to energy content and energy transfer. Heat content depends on both temperature and how much matter exists to hold that energy. A low-density gas at millions of kelvins can contain less total energy per cubic meter than a dense gas at a much lower temperature. It can also deliver less energy to a surface, because each particle impact is rare. A surface in shadow is therefore shaped mainly by what it radiates away, and by what radiation it absorbs, not by the passing hot plasma. Gravity sets the overall scale. A useful concept is virial temperature, the characteristic temperature a gas reaches when its random motion broadly balances the gravitational pull of the halo. It is not a fixed thermostat, but a guide to how deep the gravitational well is. Massive halos tend to hold hotter diffuse gas. Less massive halos tend to hold cooler gas and allow more of it to settle into denser structures. Yet even in hot halos, cooling and inflow can create colder pockets, while outflows can inject fresh energy. In the far reaches of a halo, the local starlight fades, and the few particles present cannot easily trap energy. The cosmic microwave background and the combined light of distant galaxies remain, but both are weak. This is why space around a galaxy can still be described as cold, even when the halo contains hot plasma. Coldness describes the environment's inability to share and retain heat, while the hot gas describes the speed of a sparse population of particles moving through a nearly empty volume. In the outskirts, these two truths sit together without conflict, held in place by gravity and by the quiet rules of radiation. Between the bright points of stars, the interior of a galaxy is filled with interstellar space. It is not a perfect vacuum. It holds gas, dust, and energetic particles, spread so thinly that emptiness still dominates the senses. The region is threaded by magnetic fields and crossed by light from many stars at once. It is also crossed by the galaxy's own history, because gas drifts, cools, heats, and circulates through different states. In this environment, cold is common, yet it does not appear as a single temperature or a single texture. It appears as a balance, maintained by how rarely particles meet and by how easily energy leaves as radiation. The interstellar medium is the name used for this mixture of gas and dust between stars. It is mostly hydrogen and helium, with small amounts of heavier elements. Dust grains make up only a tiny fraction of the mass, but they matter because they absorb and emit light, and they influence the electrical state of the gas. The average density is far lower than any atmosphere. Even in relatively busy regions of the galactic disk, there may be only a few atoms in a volume the size of a cubic centimetre, and in other places there may be far less. This scarcity changes every familiar intuition about heating. Interstellar gas is not all in one condition. It tends to settle into broad phases, each defined by temperature, density, and ionization, meaning whether atoms hold onto their electrons or have lost them. Some interstellar gas is cold and relatively dense by interstellar standards, with temperatures of tens to a few hundreds of kelvins. Some is warmer, around several thousand to around 10,000 kelvins, and still thin. Some is very hot, reaching millions of kelvins, in bubbles blown by supernova explosions. These phases are not stacked in layers like air above an ocean. They intermingle and overlap, filling the space between stars in a patchwork shaped by turbulence and by the uneven placement of energy sources. In the colder and warmer phases, radiation and chemistry govern the temperature. Ultraviolet light from stars strikes dust grains and can knock electrons free. This process is called the photoelectric effect, and in interstellar space it becomes a major heating mechanism. The freed electrons carry energy into the gas as they collide with atoms and ions. The efficiency depends on the dust grain's charge and composition, and on the strength of the ultraviolet field. In places where ultraviolet light is weaker, or where dust grains hold charge that suppresses electron release, heating slows. Other forms of heating remain present. Cosmic rays, which are high-energy particles accelerated by shocks and other violent events. pass through the interstellar medium and ionize atoms along their paths. Each ionization deposits energy. This heating is relatively uniform compared with starlight because cosmic rays scatter through magnetic fields and reach into regions where ultraviolet photons may be fewer. There is also heating from the formation of molecules on dust grain surfaces and from the release of chemical energy in reactions. But in the diffuse medium, these are secondary compared with the steady influence of starlight and cosmic rays. Cooling is often more efficient than heating when gas becomes denser. Cooling means the gas loses energy by emitting radiation. Atoms and ions can radiate away energy at specific wavelengths when collisions excite them to higher energy states, and they later return to lower states. In the cooler parts of interstellar space, certain ions and atoms with easily excited energy levels become especially important radiators. Their emission can fall in infrared and radio wavelengths, allowing energy to escape into space. Because interstellar space is thin, much of this radiation travels away without being reabsorbed, so cooling can be effective even when densities are low. The balance between heating and cooling creates stable temperature ranges. In many regions, gas settles into a cold neutral phase and a warm neutral phase, both largely made of hydrogen atoms that keep their electrons. The cold phase is denser and cools efficiently through radiation from trace elements, allowing it to remain cold even while it absorbs some energy. The warm phase is thinner and warmer because cooling is less effective at lower density. So the same heating processes hold the gas at higher temperature. A warm ionized phase also exists, maintained by ultraviolet photons that strip electrons from hydrogen, especially near clusters of hot stars. Each phase can exist side by side because pressure, rather than temperature alone, tends to balance across boundaries. Higher temperature gas can share similar pressure with lower temperature gas if its density is lower. The hot phase is formed by events that inject energy suddenly. Supernova shocks heat gas to extreme temperatures and create expanding cavities. In these cavities, densities drop, and the gas can remain hot for long times because radiative cooling becomes slow at such low density. The hot gas can also cool through expansion, because as it expands, it does work on its surroundings and loses internal energy. This is called adiabatic cooling, meaning cooling by expansion without the need for radiation. Yet even with these cooling pathways, the timescales can be long, leaving a volume that is hot in particle temperature while still being so thin that it transfers little heat to solid bodies passing through. In this region, temperature is a careful word. For a gas, temperature describes the average random motion of particles. A warm interstellar gas has atoms moving rapidly compared with a cold interstellar gas, but the number of atoms is so small that the total energy per cubic meter can be modest. A spacecraft in shadow does not become warm simply by passing through warm gas, because the gas cannot deliver energy quickly through collisions. Instead, the spacecraft's temperature is determined mainly by radiation. It warms when it absorbs light from stars or from nearby glowing dust and gas, and it cools when it emits infrared radiation into a sky that is largely dark. Starlight in the interstellar medium is present, but it is diluted. Even within a galaxy's disk, most of space is far from any star. Light arrives from many directions, but each star covers a tiny fraction of the sky, and most directions contain deep space. The total energy in the starlight field is therefore low compared with direct sunlight near a star. When an object is not in direct illumination, it loses energy to radiation faster than it gains it, and it drifts toward low equilibrium temperatures. The cosmic microwave background remains beneath everything, and the combined glow of stars and dust adds a little more. but the field is weak compared with the heating that occurs on sunlit surfaces. Interstellar space also shows that coldness is not an absence of activity. Gas moves in streams and eddies, clouds drift and shear, and magnetic fields guide charged particles. Yet the lack of dense matter prevents heat from behaving like it does in air. Conduction, the transfer of heat by particle collisions, is limited by the rarity of collisions. Convection, the transfer of heat by rising and sinking fluid, requires a dense fluid. An interstellar gas is too thin to act like one on human scales. Radiation becomes the dominant messenger of energy, and it carries energy away without lingering. The result is a medium that can contain both cold gas and hot gas, and still allow space itself to remain effectively cold to anything that is not directly illuminated. The interstellar medium is a place where energy is constantly exchanged, but mostly through light, and where temperature is shaped by balance rather than by proximity to a single heat source. Cold persists because matter is sparse, collisions are rare, and the sky offers an enormous sink into which radiation escapes. Within the interstellar medium, the coldest places are often the places most sheltered from light. They're not cold because they are far from stars alone. They're cold because dust and gas combine to block the main sources of heating, while still allowing energy to leave. These regions form as clouds, some diffuse and some dense, drifting through the galaxy's disk. Their interiors become quiet in a special way. Where ultraviolet radiation is weakened, chemical changes build molecules, and the remaining heat leaks away by faint, efficient emission. A cloud begins as a slight increase in density, an unevenness in the interstellar gas. Gravity pulls more material toward that unevenness, but turbulence and magnetic pressure resist and stir it. Over time, some regions gather enough mass to become distinctly denser than their surroundings. As density rises, the cloud becomes more effective at absorbing ultraviolet light. Dust grains, tiny solid particles made of carbon and silicates and other compounds, are particularly important. They intercept ultraviolet photons and visible photons. They heat up slightly and then re-radiate their energy at longer wavelengths, mostly in infrared. In this way, dust turns energetic starlight into gentler glow. The surface of a cloud is exposed. Ultraviolet photons still strike it and still liberate electrons from dust grains, heating the gas. At the surface, atoms remain more ionized and warmer. Deeper in, the story changes. Each layer of dust absorbs a portion of the incoming ultraviolet light, so the intensity drops quickly with depth. The interior receives far fewer ultraviolet photons, and the photoelectric heating that dominates diffuse space weakens. When heating weakens and cooling remains possible, temperature falls. Cooling in these clouds is aided by the very same increase in density that blocks light. Collisions become more common. Atoms, ions, and molecules bump into each other more frequently, which makes it easier to excite specific energy states that can then radiate away energy. In moderately dense clouds, certain atoms and ions radiate strongly in infrared and radio wavelengths. In denser clouds, molecules become major coolants. Carbon monoxide is one of the most important because it has rotational energy levels that are easily excited at low temperatures, and it emits at millimeter wavelengths that can escape the cloud. Other molecules and atoms contribute as well, each with its own set of lines, meaning its own specific wavelengths of emission. Dust also cools. Because dust grains radiate efficiently in infrared, they can shed absorbed energy readily. In a dense cloud, dust grains and gas molecules collide often enough that they can exchange energy, tending toward a shared temperature. When dust radiates energy away, it can pull energy from the gas through collisions, helping to cool the gas indirectly. This coupling becomes stronger as density increases. In very dense regions, dust and gas temperatures can track each other closely. As clouds become denser and colder, hydrogen begins to form molecules. Molecular hydrogen forms efficiently on dust-grained surfaces, where hydrogen atoms stick, meet, and combine. The newly formed molecule can carry away some energy, and the grain helps absorb the released binding energy. Molecular hydrogen itself is not the best radiator at very low temperatures, because its energy transitions are not easily excited in cold gas, but its presence marks a chemical shift. Once hydrogen becomes molecular, other chemistry follows. Carbon becomes incorporated into carbon monoxide, oxygen into water and other molecules in icy mantles on dust grains, and nitrogen into compounds that trace the deeper interior. The coldest dense clouds are called molecular clouds, and within them, even denser pockets form. These pockets can reach temperatures of around 10 kelvins, sometimes a little lower or a little higher depending on conditions. The reason they do not fall much lower is that heating never fully stops. Cosmic rays penetrate clouds more deeply than ultraviolet photons. They ionize atoms and molecules and deposit energy in the gas. This sets a minimum heating rate that is hard to shield against. There is also residual infrared radiation from the surrounding galaxy and from the dust in outer layers of the cloud. Even in the deep interior, some radiation remains, though it is far weaker than direct starlight. In these dense regions, cold does not mean stillness. Turbulence continues, though it can be subsonic or supersonic depending on scale and conditions. Magnetic fields thread the cloud and guide charged particles. Gravity gathers mass into filaments and cores. Yet the temperature stays low because energy escapes efficiently and is not replaced by strong external heating. The interior becomes a place where thermal motion is slow and where pressure support from heat is reduced, allowing gravity to play a larger role in shaping structure. The way cold is maintained is strongly connected to the nature of radiation in space. A dense cloud does not trap heat the way a thick blanket traps warmth in a room. In a room, a blanket slows heat flow by stopping convection and reducing conduction. In a cloud, there is no convection in the ordinary sense, but radiation is still a major pathway for energy loss. Dust re-radiates absorbed energy, and much of that infrared radiation can escape because infrared wavelengths interact less strongly with dust than ultraviolet does. The cloud is therefore a filter. It blocks high-energy photons that would heat and ionize the interior, but it allows lower-energy photons, including its own emission, to leak out. This one-way character helps the cloud stay cold. At very high densities, some infrared radiation can be trapped, and cooling can slow. The cloud can become optically thick even in infrared, meaning photons have difficulty escaping. In those cases, temperatures can rise as collapse proceeds, especially in the centers of forming stars. Yet that change belongs to later, deeper regions. In the cloud stage itself, before collapse becomes extreme, the dominant impression is of cold, sheltered interiors maintained by dust shielding and efficient emission. A drifting object passing near such a cloud experiences the same general truth that appears throughout space. Unless it is struck by direct starlight, it cannot draw much warmth from the surrounding gas. The cloud's gas may be denser than the general interstellar medium, but it is still thin compared with air, and it does not carry heat well by contact. The object's temperature is set mostly by radiation. If it sees the cold sky and the faint infrared glow of dust, it tends to cool. If it enters a shadowed region near a dense cloud, its view of bright stars may shrink further and it cools more readily. The cloud, in this way, becomes not only a reservoir of cold gas but also a demonstration that cold in space is protected by distance and by the selective filtering of light. In the dust-shielded interiors, space becomes cold not because energy is absent, but because energy has an easy route outward and few strong routes inward. The cloud is a structure built from scarcity, where a small rise in density changes the rules of heating, and where radiative loss keeps the interior near the lowest temperatures the galaxy commonly supports. The Sun travels through the Milky Way inside a local patch of interstellar space that is unusual in density and in structure. Around the solar system lies a broad cavity known as the local bubble, and within that cavity lies a smaller concentration of gas and dust, often called the local interstellar cloud. These nearby regions show how space can remain cold in a practical sense, even when the surrounding gas is warm or even extremely hot, because temperature alone does not guarantee that heat can be stored or shared. The local bubble is a low-density cavity in the interstellar medium, extending for roughly a few hundred light-years in some directions and less in others. Its boundary is irregular, shaped by overlapping shells and by the patchwork of nearby clouds. Observations indicate that much of its interior contains very thin plasma, with temperatures on the order of 1,000,000 kelvins. The common explanation links the cavity to multiple supernova explosions and strong stellar winds within the past several million years, which push interstellar gas outward and leave behind a hot, rarefied interior. The exact sequence and timing remain uncertain, because the evidence is dispersed and mixed, but the broad mechanism is consistent with how similar cavities form elsewhere in the galaxy. 1,000,000 kelvins suggests intense heat, yet the local bubble remains an environment where cold dominates for solid objects that are not directly lit. The reason is density. When a gas is extremely thin, it holds little total thermal energy per unit volume. Its particles move rapidly, but there are too few of them to deliver energy by frequent impacts. Collisions are so rare that the gas cannot act like a warm bath. A surface drifting through it receives only occasional particle strikes, and most of its energy exchange occurs through radiation, not through contact. Radiation in this region is present but faint. Starlight from nearby stars crosses the cavity, and the broader glow of the Milky Way adds a diffuse background. The cosmic microwave background remains beneath everything as a nearly uniform field. The hot plasma can emit high-energy radiation, but the overall energy density in that emission is small compared with the energy density in direct sunlight near a star. In the absence of direct illumination, an object loses energy by emitting infrared radiation into a sky that is mostly dark, and it gains energy only slowly from the weak surrounding glow. Its equilibrium temperature therefore remains low, even while the local plasma is hot in the sense of particle motion. Inside the local bubble, the Sun sits in a smaller region of warmer and denser gas. This local interstellar cloud is partially ionized, meaning that some atoms have lost electrons while others remain neutral. Its temperature is commonly measured at around several thousand kelvins, with estimates near 7,000 kelvins for the gas that flows past the solar system. Its density is still extremely low, on the order of fractions of an atom per cubic centimeter for neutral hydrogen, with additional contributions from ions and electrons. Compared with the bubble plasma, it is denser and cooler, yet compared with any atmosphere, it is almost empty. The cloud's temperature is maintained by a balance of heating and cooling. Ultraviolet radiation from hot stars and the general galactic field ionizes atoms and deposits energy in freed electrons. Cosmic rays also ionize gas and supply a steadier background of heating that penetrates more uniformly. Cooling occurs when collisions excite atoms and ions, and the gas emits radiation at specific wavelengths that escape into space. Trace elements such as carbon and oxygen are important in this cooling, because their ions have energy transitions that radiate efficiently at these temperatures. Dust grains absorb some starlight and re-radiate in infrared, shaping both the radiation field and the thermal balance of the gas. The local cloud persists within the hotter cavity partly because heat does not flow freely through interstellar space. Magnetic fields thread the local medium and guide charged particles, limiting how efficiently energy can be conducted from hot plasma into cooler gas across field lines. Boundaries between phases can therefore remain relatively sharp, allowing warm clouds to survive inside a hotter, thinner environment. Observations of absorption lines toward nearby stars indicate that the local region is not a single uniform cloud, but a collection of nearby cloudlets with slightly different velocities and ionization states embedded within the broader cavity. For objects in this neighborhood, the gas temperature is not the main driver of their own temperature. Conductive heating from the gas is weak because the gas is too thin, even in the local cloud. Instead, the controlling factor is radiative exchange. A surface warms mainly when it absorbs light, and it cools mainly by emitting infrared radiation. If it is illuminated by a nearby star, it can become warm, and if it is shaded from bright sources, it cools toward an equilibrium set by the diffuse galactic glow and the cosmic microwave background. The same neighborhood can therefore contain warm gas and cold objects at the same time, without contradiction. The scarcity of collisions also affects how information travels through the medium. Neutral atoms can move long distances before colliding, and their flows preserve the imprint of local temperatures and motions. Measurements of neutral helium entering the solar system, together with remote observations of nearby stars, help constrain the properties of the local cloud. These data reinforce a simple physical fact. In a very dilute gas, temperature describes particle motion, but it does not guarantee that heat will be transferred efficiently to anything else. The sun's neighborhood in the local bubble is therefore quiet in a particular way. A large volume holds plasma that is hot but thin, threaded by magnetic fields and diluted by expansion. Within it lie warmer cloudlets that are denser but still almost empty, with temperatures regulated by faint radiation and by efficient line cooling. Across both, radiation remains the dominant pathway by which energy is gained and lost by solid bodies. Coldness persists because the environment lacks the density needed to store warmth and lacks the mechanisms that spread heat quickly in ordinary fluids. In this local interstellar setting, space remains a place where energy passes through easily and lingers only where matter is close enough to hold it. At the edge of the solar system, the influence of the sun meets the influence of interstellar space in a boundary region shaped by flowing plasma. The sun continually releases a stream of charged particles called the solar wind. This wind expands outward in all directions, carrying with it the sun's magnetic field in a stretched and twisted form. Far from the sun, the solar wind slows and interacts with the surrounding interstellar medium, creating a transition that ends at the heliopause, the boundary that separates solar wind plasma from interstellar plasma. In this region, the meaning of temperature becomes more layered, and the idea that space is cold even near the sun becomes clearer through the difference between hot particles and cold surroundings. The solar wind begins as hot plasma in the sun's outer atmosphere. It accelerates outward, becoming supersonic, meaning it travels faster than the speed of sound in that plasma. Yet as it expands, its density falls rapidly. The same number of particles spreads over ever larger spheres. The wind remains plasma, a state in which electrons are free from nuclei, and it carries energy in several forms, the bulk flow of particles moving outward, the random motion of particles that defines temperature and magnetic energy in the carried field. As the solar wind travels outward, it cools in a broad sense through expansion. When a gas expands without gaining heat from outside, its temperature falls because energy is used to do work in pushing outward. In the solar wind, the details are complicated by magnetic fields, waves, and collisions that are infrequent. Different particle populations can have different temperatures. Protons, electrons, and heavier ions do not always share the same thermal state because their collisions become too rare to force equilibrium. Temperature, in this plasma environment, can describe different directions as well, with motion along magnetic field lines differing from motion across them. Despite these complexities, a general trend holds. The solar wind becomes cooler in its particle temperatures as it travels outward, though not simply by the same rule that governs an ideal gas in a laboratory. The wind also remains extremely thin. Even in the outer solar system, a cubic centimetre may contain only a few particles. This thinness means that, while the solar wind is a moving river of particles, it does not behave like hot air. It cannot easily warm a surface by contact because particle impacts are too infrequent to deliver much energy. Where the solar wind first begins to feel the resistance of the interstellar medium, it forms a shock called the termination shock. A shock forms when a fast flow is forced to slow quickly. At the termination shock, the solar wind decelerates from supersonic to subsonic, and some of its directed motion converts into random motion. This increases the thermal energy of particles, and in that sense the plasma becomes hotter, yet the density remains low. The shock region is not like a furnace. It is a rarefied zone where particles carry more energy individually, but their ability to share that energy with objects is still limited. Beyond the termination shock lies the heliosheath, a region of slower, hotter, and more turbulent solar wind plasma. Here, the sun's magnetic field is compressed and stirred. Energetic particles can be accelerated, and the plasma can show complex flows as it is diverted around the heliopause. In the heliosheath, temperature again is not a single number shared by all particles. Protons and electrons may differ, and the distribution of particle speeds can deviate from simple thermal shapes because collisions remain scarce. Yet as a broad description, the heliosheath contains plasma that is hotter than the solar wind upstream of the termination shock. At the outer edge of the heliosheath lies the heliopause. This boundary is not a solid wall, it is a surface where pressure balances, and where the sun's outward flow is held back by the pressure of the interstellar medium. On one side, the plasma is dominated by particles originating from the sun. On the other side, it is dominated by interstellar plasma and neutral atoms. Magnetic fields on both sides influence how sharply the boundary forms and how much mixing occurs. Some mixing is expected in the form of instabilities and reconnection events, but the overall separation persists because the flows and fields maintain a balance. This boundary region highlights a central reason why space stays cold. Temperature in a plasma can be high, but the heat content and heat transfer can still be low if density is low. A hot plasma with only a few particles per cubic centimetre contains little energy per cubic metre, compared with a dense gas at a much lower temperature. It also delivers that energy to a surface slowly, because there are few impacts. Meanwhile, a surface radiates away energy continuously in infrared. If that surface is not absorbing sunlight, it cools. The surrounding plasma does not prevent that cooling, because it does not provide a strong flow of heat back into the surface. The heliopause region also shows the difference between particle temperature and radiative environment. The plasma temperature describes particle motion, but a spacecraft's thermal balance depends largely on the radiation it absorbs and emits. Far from the sun, sunlight is weak. The dominant radiation fields become the cosmic microwave background and the diffuse glow of the galaxy. A spacecraft in shadow, even while immersed in plasma with energetic particles, tends toward a low equilibrium temperature set by those radiation fields and by its own emissivity, meaning how effectively it emits thermal radiation. There is also a population of neutral atoms that cross the boundary. Neutral atoms are not bound to magnetic fields, so they can pass through the heliopause more freely than charged particles. Some neutral atoms from interstellar space enter the heliosphere and become ionized by sunlight or by collisions, becoming pickup ions that are then swept along by the solar wind. This exchange adds complexity to the particle populations and the energy balance, yet does not change the basic radiative truth. The overall region remains so thin that radiative exchange dominates temperature control for solid objects. The outer heliosphere, therefore, is a place where the Sun's influence is extensive in terms of particle flow and magnetic fields, but limited in terms of warming the emptiness. The solar wind carries energy outward, but it does not fill space with warmth the way air fills a room. It becomes thinner and less able to heat by contact as it expands. At its boundary, shocks and turbulence can raise particle temperatures, but they do not create a warm environment for objects in shadow. Cold remains the default, because the vacuum offers little capacity to store heat, and because radiation remains the primary path for energy to leave. In this outer boundary, the solar system's edge forms a quiet demonstration that even near a star's domain, space itself does not become warm without matter and without light falling directly on surfaces. Beyond the heliopause, distance continues to thin the sun's light, and the solar system's small bodies begin to dominate the scene. The Kuiper belt occupies a broad zone outside Neptune, where countless icy objects travel in slow orbits. Some are large enough to be rounded by their own gravity, with varied surfaces and brief, tenuous atmospheres. Many more are small and dark, shaped by collisions and by long exposure to radiation. In this region, space is cold in a direct, practical sense, because sunlight is weak, shadows are deep, and the empty volume between objects offers almost no way to store or share warmth. The sun remains the main external energy source, yet its radiative power spreads over a sphere that grows with distance. Each doubling of distance spreads the same light over 4 times the area, so the available energy per square meter falls quickly. Near the Kuiper belt, distances commonly range from about 30 to 50 astronomical units from the Sun. At such distances, sunlight is faint compared with the inner solar system, and it is easily outmatched by a surface's ability to radiate heat away. Warming becomes local and temporary, tied to whether a patch of ground faces the sun at a given moment. A surface here tends toward an equilibrium temperature set by absorbed sunlight and emitted infrared radiation. Absorbed sunlight depends on reflectivity. A bright surface sends much of the incoming light back to space, reducing heating. A dark surface absorbs more and warms more. Emission depends on emissivity, a measure of how effectively a surface radiates. Many natural materials radiate well in infrared, so once they gain energy, they also lose it efficiently. Because sunlight is weak, equilibrium temperatures often lie far below the freezing point of water, commonly around a few tens of kelvins to around 100 kelvins, depending on distance and surface properties. Cold does not make surfaces uniform. Rotation creates day and night cycles, even if days are long. As an object turns, a sunlit patch warms and then cools again in shadow. The depth to which this warmth penetrates depends on thermal inertia, which reflects how readily a material stores and conducts heat. A fluffy, porous layer can act as insulation. It warms quickly at the surface but conducts little heat downward, leaving the interior colder and more stable. A denser surface spreads heat more effectively and smooth swings, but the limited sunlight and constant radiative loss keep average temperatures low. Many Kuiper belt objects are coated with ices stable only in cold conditions. Water ice is common, and other ices can persist as well, including methane and nitrogen. These substances tend to sublimate at different temperatures. In the Kuiper belt's cold, some of these ices remain solid for long periods, yet small changes can still matter. When sunlight reaches a region for longer, or when an orbit carries an object slightly closer to the Sun, a thin surface layer can warm enough for molecules to leave. Those molecules may escape to space or freeze again in colder areas, slowly shifting frosts across the landscape. Pluto illustrates how low temperatures can still support change. Its surface holds nitrogen ice and methane ice, and it supports a very thin atmosphere that varies with season as parts of the surface warm and cool. The temperatures remain extremely low, yet changes around those values can alter whether nitrogen stays frozen or becomes gas. The atmosphere is too tenuous to hold heat the way a dense atmosphere does, but it can move molecules and deposit frost where condensation is favored, making the surface a record of sunlight and shadow. The surrounding vacuum remains indifferent. There is no air to spread warmth from a sunlit patch to a shaded patch. Heat moves through the solid body by conduction, and it leaves the surface by radiation. Conduction is slow when materials are porous or layered with frost, and radiation is relentless because the surface faces a sky that returns little energy. The cosmic microwave background and the diffuse glow of the galaxy remain present, but their contribution is small compared with even the weak sunlight and far smaller than the infrared emission of a warmed surface. The contrast between sunlit and shadowed ground can therefore be sharp, especially along steep slopes and within deep hollows. Cold also shapes what happens to any gas that is released. At low temperatures, many gases freeze readily onto surfaces. A molecule that leaves a warmer patch may follow a simple arc under gravity and settle onto a colder region and stick. Without a dense atmosphere, there is little mixing and little buffering. Frosts collect where the energy balance favors them, and darker or brighter materials alter that balance by changing how much sunlight is absorbed. Even the particles that drift through this region do not change the thermal picture. The solar wind is still present, though weakened and altered by distance and by interaction near the heliopause. Interstellar atoms and ions also pass through. Some of these particles can be energetic, but their densities are so low that they deliver little heat by impact. For most surfaces, the steady exchange is between sunlight, infrared emission, and the faint background glow. Larger bodies carry a small internal heat source from radioactive elements in their rocky material, and that heat can slowly leak outward, but the surface remains controlled by radiative balance. In deep, persistent shadow, temperatures can fall toward the coldest values allowed locally, creating stable cold traps for volatile ices. A spacecraft passing through the Kuiper belt experiences the same rule. Its temperature depends mainly on radiation, on orientation, and on how it handles internal heat from its systems. In shadow, it radiates energy away into a nearly black sky and cools. In sunlight, it warms quickly. The surrounding space does not provide a gentle background temperature because there is almost nothing to touch it and almost nothing to carry heat across distance. The Kuiper belt is a region where cold is a governing condition. Weak sunlight sets low equilibrium temperatures. Porous surfaces trap cold beneath thin layers, and the vacuum prevents heat from spreading by anything other than slow conduction and radiation. Space stays cold not because the sun is absent, but because its energy arrives as light that thins with distance, and because nothing in the emptiness holds that energy in place once it is emitted back into the dark. Across the region of the giant planets, the solar system looks populated, yet the space between objects still behaves like emptiness. Jupiter, Saturn, Uranus, and Neptune move through wide orbits separated by hundreds of millions of kilometers. Their moons form miniature systems of rings, dust, and plasma. All of it exists inside a volume where sunlight is already weak, where shadows are deep, and where heat does not spread by air or water. Warmth appears only where matter intercepts light or produces its own energy, and the surrounding vacuum remains largely unchanged. Sunlight at these distances arrives as a diluted beam. By the time it reaches the orbit of Jupiter, the sun's radiation is only a small fraction of what it is near Earth. The energy per square meter falls with the square of distance, so sunlight can warm a surface that faces it, but it cannot keep a broad region of space warm. The gaps between moons stay thermally empty. It strikes surfaces, heats them locally, and those surfaces re-radiate energy away. A body in this region settles toward an equilibrium temperature set by what it absorbs and what it emits. The giant planets illustrate this balance in a layered way. Their upper clouds receive weak sunlight, but they also emit thermal infrared radiation. Jupiter and Saturn, and to a lesser extent Neptune, radiate more energy than they receive from the sun, indicating an internal heat source. That internal heat comes from energy left over from formation and from slow gravitational contraction. Released as the interior settles, Uranus shows much less excess emission, suggesting that its internal heat escapes less efficiently or is smaller. These differences drive weather and circulation, yet they do not warm surrounding space in any widespread way, because radiation thins out quickly and the vacuum does not hold it. Near each planet, warmth becomes noticeable only through proximity and line of sight. A spacecraft near Jupiter sees the Sun as a bright but smaller disk, and also sees Jupiter itself as a large, glowing body in infrared. If the spacecraft faces the planet, it absorbs some of that infrared radiation and some reflected sunlight. If it passes behind the planet, sunlight is blocked and the spacecraft cools in shadow, while still receiving a weaker infrared glow from the planet and from nearby ring or moon surfaces. The effect is local and geometric. It depends on what the spacecraft can see, not on any ambient warmth of the surrounding space. The moons show the same rule. Many are cold, with surfaces dominated by water ice and darker compounds. Their temperatures depend on weak sunlight and on how quickly they radiate heat away. In long-lived shadow, frost can persist because incoming radiation is limited. In sunlit regions, ice warms modestly and then cools again as rotation and eclipses bring night. Some moons add their own energy through tides. Io is heated by tidal flexing and loses energy through volcanism. Europa and Enceladus are warmed internally enough to maintain subsurface liquid water beneath ice shells. Internal heating can raise local surface temperatures near active regions and drive plumes of gas and ice, yet the warmth does not spread through space. Material ejected into vacuum expands and cools, and radiation from warm patches fades with distance. Saturn's rings sharpen the same principle. The rings are made of countless icy particles, each one absorbing sunlight, receiving infrared from Saturn and emitting infrared back to space. Parts of the rings in Saturn's shadow cool quickly. Parts in sunlight warm, but only to temperatures consistent with weak solar heating and efficient emission. The ring system does not create a warm zone around Saturn. It forms a thin plane of particles whose temperatures vary with illumination and with how much of Saturn fills their sky. Around the giant planets, magnetospheres add another kind of heat that is mostly irrelevant to comfort. Planetary magnetic fields trap charged particles and guide them into belts and currents. Those particles can be energetic, and in that sense the plasma can be hot. Yet densities remain extremely low, so it transfers little heat by contact. Its main effects are electrical and chemical, altering thin atmospheres, charging dust, and driving auroras where particles enter upper atmospheres. The surrounding vacuum does not become warm because a hot plasma with few particles cannot deliver much energy to surfaces compared with what those surfaces steadily lose by infrared emission. When heat transfer is considered carefully, the reason for cold becomes straightforward. Conduction through gas is negligible because there is almost no gas. Convection is absent because it requires a dense fluid. Radiation remains the primary pathway. Radiation can warm only what it strikes, and it can cool anything that emits. A spacecraft, a ring particle, or an icy moon exchanges energy mainly by photons. If illuminated, it warms. If shaded, it cools. It does not carry warmth outward to nearby empty space because there is no medium to carry it, and its own radiation spreads outward and becomes weak with distance. The planets themselves emit strongly in infrared, but that emission does not change the baseline far away. Close to Jupiter or Saturn, the planet's infrared can noticeably affect an object's equilibrium temperature, especially if the object absorbs well at those wavelengths. Farther away, the planet fills a smaller fraction of the sky, and its influence falls. The same is true for reflected sunlight. A bright planet acts as a secondary lamp, only for nearby moons and spacecraft. Beyond that local neighborhood, the scene returns to darkness, faint starlight, and the cosmic microwave background. Cold also appears through the behavior of materials. Ices are stable on many moons because temperatures remain low for long periods. Gases are rare on most bodies because low gravity and heating by sunlight and energetic particles allow molecules to escape, where tenuous atmospheres exist. They're too thin to distribute heat widely. Night sides cool efficiently, day sides warm modestly, and the overall temperature remains governed by radiative balance. In the giant planet region, the sun is still present, and large planets hold deep reservoirs of internal heat. Yet the open vacuum between them remains cold because heat is not a substance that fills space. It is energy that must be carried, and here it is carried mainly by light and by sparse particles that seldom collide. Warmth is real on sunlit surfaces, in thick atmospheres, and in tidally heated interiors. The coldness of space persists around all of it as the steady outcome of dilution and of radiation escaping easily into the dark. Between the orbits of Mars and Jupiter, the solar system holds a wide band of small worlds. The asteroid belt is not a continuous ring of rock, but a scattered population of bodies separated by immense distances. A few are large enough to be roughly spherical. Many are irregular, and countless more are fragments produced by impacts. The volume they occupy is so large that emptiness still dominates. This region sits closer to the sun than the giant planets do, and sunlight is stronger here, yet space remains cold in the same essential way. Warmth attaches to material that absorbs light, while the space between those materials has little capacity to hold heat. An asteroid's surface temperature is set mainly by radiative balance. Sunlight arrives as a stream of photons. The surface absorbs a portion of that light, depending on its reflectivity, and the absorbed energy becomes internal motion of atoms in the upper layers. The surface then sheds that energy by emitting infrared radiation. In the asteroid belt, the Sun's brightness is reduced compared with Earth's orbit, yet it remains strong enough to warm sunlit rock far above the levels found in the outer solar system. The exact temperature depends on distance, rotation, and surface texture. Darker asteroids absorb more light and warm more. Brighter surfaces warm less. Many asteroids are coated in regolith, a layer of broken rock and dust that conducts heat poorly. Such a surface can heat quickly in sunlight and cool quickly in shadow, while deeper layers change more slowly. Even here, the vacuum between asteroids does not become warm simply because sunlight passes through it. Sunlight carries energy, but it does not deposit that energy unless it is absorbed. Most photons travel through space without interacting. When a photon is absorbed by a surface, the surface warms locally. When that surface emits infrared photons, those photons also travel freely, spreading into larger and larger volumes. The emitted energy becomes diluted with distance. Space does not fill with warmth. It remains a pathway for radiation rather than a storehouse for it. The day and night cycle on an asteroid can be sharp. Many asteroids rotate in hours, and their lack of thick atmospheres prevents heat from being redistributed. A sunlit slope can warm while a shaded crater wall remains much colder. When an asteroid turns, the warmed surface radiates energy away into a sky that returns little infrared. Temperatures drop after sunset. The contrast is stronger on bodies with low thermal inertia, where the surface cannot store much heat from one moment to the next. In fractured terrain, cracks and pits can remain in persistent shade for long intervals, holding colder conditions than nearby sunlit ridges, not because cold flows into them, but because radiation out exceeds radiation in. Impacts in the belt continually create fine debris. Collisions grind rock into dust grains ranging from visible specks down to microscopic sizes. Over time, this dust becomes part of a broader flattened cloud concentrated near the plane of planetary orbits. Seen from within, it can scatter sunlight and produce the faint zodiacal light along the sky's broad midline. The glow is not a sign that space is warm. It is simply sunlight redirected by innumerable particles. Each dust grain behaves like a tiny thermal world. It absorbs and scatters some sunlight, and it emits infrared radiation. Its equilibrium temperature depends on distance from the sun, on composition, and on size. Small grains can absorb sunlight efficiently, while emitting infrared less efficiently at some wavelengths, which can raise their temperatures above what an ideal blackbody would suggest. Other grains reflect more and remain cooler. There is little sharing of heat by contact. Collisions between grains are rare, and there is almost no gas to conduct energy. Each grain largely follows its own balance between absorption and emission. The same radiative processes that set temperature can also apply gentle forces. When a body absorbs sunlight and later emits infrared, the timing and direction of that emission can create a tiny push, especially for small, irregular objects whose warm afternoon side emits more strongly than the cool morning side. Over long periods, such effects can alter the paths of the smallest asteroids and fragments, adding another slow mechanism that reshapes the belt. These forces remain subtle compared with gravity, yet they matter because the belt is an environment where tiny influences can accumulate over immense time. The dust population is also shaped by the gentle forces carried by sunlight. Radiation pressure provides a small outward push, especially important for the tiniest grains. Another slow effect, Poynting-Robertson drag, causes grains that absorb and re-radiate sunlight while orbiting to lose a little orbital energy and drift inward over long times. These processes remove dust and reshape the cloud. New dust is continually supplied by fresh impacts among asteroids and by material released from comets that cross the region. The cloud persists through turnover rather than permanence. The zodiacal dust shows how warm and cold can coexist in the same thin volume. A grain in direct sunlight can be warm in the sense that its temperature stands far above the cosmic microwave background. Nearby emptiness remains cold because it does not store the grain's heat. Infrared photons leave the grain and stream away, quickly spreading through space. The mass available to hold thermal energy is tiny, and the energy that is radiated away is not trapped. The overall environment remains dominated by radiative exchange and by dilution. For spacecraft, the asteroid belt makes the same rule tangible. A vehicle's temperature is not set by the temperature of the surrounding vacuum, because the vacuum offers almost no conductive heating or cooling. The vehicle warms by absorbing sunlight and by absorbing infrared from nearby sunlit surfaces, and it cools by radiating infrared to deep space. Near an asteroid, the asteroid can add local infrared, but the effect fades quickly with distance. Far from any surface, the thermal balance is controlled mainly by the spacecraft's orientation to the Sun and by how efficiently it emits radiation. In this region, sunlight can still warm rock, dust, and metal, but it does not warm space itself. Heat moves chiefly as light. Matter is too sparse to spread energy by collisions, and emitted radiation disperses into larger volumes without returning. The asteroid belt and its dust cloud hold countless small surfaces that brighten and cool in cycles, while the surrounding emptiness stays a dark sink that steadily accepts their infrared emission. Near Earth's orbit, the Sun's light is strong, and the planet itself becomes a large radiant presence. Yet the space around Earth remains a place where cold dominates whenever a surface stops absorbing light. The reason is not mystery or distance. It is the way energy moves when there is almost no air to hold it, and the way a surface must balance what it absorbs with what it emits. Earth orbits within a stream of sunlight that arrives from one direction. In open space near Earth, that sunlight is intense and steady unless an object passes into shadow. A sunlit surface can warm quickly, because it is struck by photons that carry energy directly into the material. The warmed surface then emits infrared radiation in response, sending energy away in all directions. If absorption exceeds emission, temperature rises. If emission exceeds absorption, temperature falls. This balance, called radiative equilibrium, sets the temperature of most objects in orbit more than any contact with surrounding matter. The surrounding matter is extremely thin. Even in low Earth orbit, above most of the atmosphere, there remains a trace of gas in the uppermost layers. This gas is enough to create drag over time and to produce chemical effects on surfaces, but it is far too sparse to behave like air at the ground. It does not spread heat around a spacecraft as wind does around a building. It does not hold warmth in place. Collisions between gas particles and a surface occur. Yet the number of impacts is small compared with the constant flow of energy by radiation. For thermal behavior, the orbiting environment resembles vacuum far more than it resembles a thin breeze. Earth itself adds two important sources of radiation. One is reflected sunlight. A portion of the sunlight that strikes Earth is reflected back to space by clouds, ice, land, and ocean. The fraction reflected is called albedo. Earth's average albedo is about 3/10, meaning that roughly 3/10 of incoming sunlight is redirected rather than absorbed. This reflected light is brightest on the day side and weakest on the night side. A spacecraft near Earth can be warmed not only by direct sunlight, but also by this reflected glow, sometimes called Earth shine. It is still sunlight in origin, but it arrives from a broader part of the sky and varies with cloud cover and viewing geometry. The second source is Earth's own thermal emission. Earth absorbs sunlight and then re-radiates much of that energy as infrared radiation. This infrared comes from the surface and lower atmosphere and spreads outward. To a spacecraft in low orbit, Earth can fill a large fraction of the sky, so the infrared radiation becomes a steady thermal input, even when the spacecraft is in Earth's shadow relative to the Sun. The planet acts as a warm lamp in infrared, not because space is warm, but because Earth is a massive body holding heat and continually emitting it. The night side still emits infrared, though the amount can vary with surface temperature and cloud patterns. Because of these competing inputs, a spacecraft's temperature near Earth is strongly controlled by orientation and by what it can see. A surface pointed toward the Sun absorbs intense sunlight. A surface pointed away from the Sun may absorb little sunlight, but it may still receive infrared from Earth if Earth is within its view. A surface that looks out toward deep space sees a sky that returns very little radiation, so it becomes an efficient path for cooling. The same spacecraft can therefore have warm and cold parts at the same time, not because the surrounding space has different ambient temperatures, but because different parts of the spacecraft face different radiation fields. Shadow plays a central role. When a spacecraft passes behind Earth, direct sunlight can be blocked for a portion of each orbit. During this eclipse, the main heating term from the Sun disappears. The spacecraft continues to radiate infrared, and unless it has other heat sources, its temperature falls. In low Earth orbit, eclipses can occur frequently, and the rapid alternation between sunlight and shadow creates repeated thermal cycling. A spacecraft's temperature does not instantly drop to the coldest possible values because it has thermal mass, meaning it stores heat in its materials, and because Earth's infrared emission continues to provide some warming. Still, the direction of change is clear. Without sunlight, radiative loss tends to dominate, and the environment behaves as a cold sink. The idea that space is cold is therefore compatible with the fact that some spacecraft can overheat. Overheating occurs when absorbed radiation and internal heat sources exceed the ability to shed energy by emission. Electronics generate waste heat. Motors, batteries, and transmitters release energy. In vacuum, there is no convecting air to carry that heat away, so it must move through the spacecraft structure by conduction and then leave by radiation. Conduction. The transfer of heat through direct contact in solids can be engineered with heat pipes, straps, and conductive paths, but it still must end at a radiating surface. The final step is always emission into space. Radiators exploit the coldness of the background. A radiator is a surface designed to emit infrared efficiently, often pointed toward deep space and away from the Sun and Earth when possible. Its temperature adjusts so that emitted power balances the heat it receives from inside the spacecraft and from external radiation. If the radiator sees deep space, it can cool effectively, because deep space provides little incoming radiation. If the radiator instead faces Earth, it receives Earth's infrared and may warm, reducing its ability to remove heat. Thermal control therefore becomes a geometric problem as much as a materials problem. Surface properties matter. Absorptivity describes how well a surface absorbs incoming radiation at certain wavelengths. Emissivity describes how well it emits infrared radiation. A surface that absorbs sunlight strongly but emits infrared poorly tends to run hot in sunlight. A surface that reflects sunlight well and emits infrared well tends to stay cooler. Coatings, paints, and multilayer insulation are used to tune these behaviors. Multilayer insulation reduces the exchange of radiation between spacecraft components by reflecting infrared and limiting radiative coupling, helping keep internal temperatures stable. Yet even with insulation, the spacecraft still must release its heat eventually, usually through dedicated radiators. Earth orbit also provides a reminder that temperature can be misunderstood when applied to space itself. The vacuum has no temperature in the ordinary sense because it has almost no particles to carry thermal motion and to collide with the surface. Instead, a temperature is experienced through radiation, through the balance of incoming and outgoing photons. In orbit, the radiation environment includes the sun's beam, Earth's reflected light, Earth's infrared emission, and a faint background from the rest of the sky. The coldness of space refers to the low level of that background and to the ease with which an emitting surface can lose energy when it faces away from bright sources. Even small changes in orbit can alter the thermal picture. At higher altitudes, Earth fills less of the sky, so its infrared contribution weakens and deep space dominates a larger fraction of the view. In such cases, a shaded surface can cool more efficiently. At lower altitudes, Earth fills more of the sky, and its infrared warms shaded surfaces more strongly, creating a gentler floor that prevents extreme cooling, but also makes it harder to reject internal heat. Across all these cases, the same physical rule applies. Without a dense medium, heat does not spread by air. It is either stored in matter, conducted through solids, or radiated away. Near Earth, the sun is not distant and the planet is close, yet space remains cold because the emptiness does not hold warmth. Sunlight and earthlight can warm whatever they strike, and internal machinery can generate heat that must be managed. But the surrounding vacuum remains a place where energy leaves easily as infrared. Temperature in orbit is a moving balance of sightlines, surface properties, and steady emission into a dark background that absorbs without resistance. Inside Earth's orbit, sunlight grows harsher. The inner solar system is still mostly empty, but the emptiness is flooded by a brighter beam. The closer a surface comes to the sun, the more energy it can absorb each second, and the faster it can warm. Yet the surrounding space does not turn into warm air. It remains a vacuum where heat is not stored and not carried by bulk motion. Cold persists whenever a surface stops absorbing radiation, because the exchange remains between incoming light and outgoing infrared. Distance in this region is often described with the astronomical unit, the average distance between Earth and the Sun. Venus orbits at about 0.72 astronomical units, and Mercury at about 0.39 astronomical units. At these distances, the sunlight per square meter rises sharply compared with Earth's orbit, because the same solar power is spread over smaller spheres. A drifting object sees the sun widen in the sky, while most other directions remain dark. On a sunlit surface, stronger sunlight changes the balance quickly. Absorbed radiation turns into internal energy, raising temperature until emission catches up. Emission increases strongly as temperature rises, so a warm surface sheds energy rapidly. But near the sun, the incoming supply can maintain high temperatures in daylight. Space remains a sink for infrared energy, while sunlight can drive exposed material toward high temperatures. The coldness is not the absence of a heat source. It is the absence of a medium that holds heat in place. Mercury shows how intense illumination can coexist with deep cold in shadow. Mercury has almost no substantial atmosphere. Without a thick blanket of gas to spread energy, its surface temperature follows the sun and the night. Under direct sunlight, sunlit ground can reach temperatures around 400 degrees Celsius. When Mercury rotates into night, the same ground radiates its heat into space and cools dramatically, reaching temperatures around -180 degrees Celsius in darkness. Long nights allow much of the stored warmth to leave because there is no dense air above it to slow the loss by convection and no thick cloud cover to return infrared radiation. The strongest contrasts occur where sunlight never reaches. Near Mercury's poles, the sun stays low, and some crater floors remain in permanent shadow. These shadowed pockets can persist at low temperatures for very long times, forming cold traps in a cold trap. Molecules that arrive as vapor can freeze and remain stable because the surface rarely warms enough to release them. Observations indicate that water ice can survive in such polar shadows despite Mercury's closeness to the Sun. The explanation lies in geometry. The Sun's heat arrives as light that must strike a surface to warm it, and a surface that never sees the Sun can remain cold even in the inner solar system. Venus offers a different lesson. It also lies closer to the Sun than Earth does, yet its surface heat is dominated by its dense atmosphere. The thick air traps infrared radiation and moves energy around the planet, so the surface stays hot even when sunlight varies with location and time. Above that atmosphere, the surrounding vacuum still behaves by radiative rules, and an object's temperature still depends on what it absorbs and what it can emit. For spacecraft, the inner solar system turns thermal balance into a problem of direction. Warming comes mainly from direct solar radiation and, during close passes, from reflected and emitted radiation from planets. Cooling comes mainly from infrared emission to deep space. As sunlight strengthens, spacecraft rely on reflective blankets and sunshields to reduce absorption, and on radiators placed where they can face darkness. Heat produced inside the craft must travel through solids by conduction to those radiating surfaces. The materials themselves set the outcome. A dark, rough coating absorbs more sunlight than a pale, reflective one. A surface that emits infrared efficiently can shed heat faster, while a low-emitting surface can trap heat within the structure. Even the angle matters, because a tilted surface intercepts less sunlight than one that faces the sun directly. A small change in orientation can shift temperatures by large amounts. The inner solar system also contains a brighter haze of interplanetary dust than the outer regions do. Sunlight scattered by this dust contributes to a diffuse brightness along the plane of the planets and nearer the sun in the sky. The dust grains themselves warm and emit infrared, but they remain far too sparse to create a warm surrounding medium. Their glow shows that radiation can be present everywhere, while space remains a poor container for heat. This region shows why a single ambient temperature is a poor description. A sunward face can run hot while a spaceward face remains cool, even when they are separated by only a small distance. The difference is not the vacuum between them. The difference is their view of the sun and their ability to shed energy by emission. When a craft enters shadow, the main external heating term vanishes while emission continues and temperatures fall. Nearer the sun, the swing between sunlight and shadow can be sharper because the beam is stronger. Even close to the sun, the vacuum itself provides little heat transfer by contact. A surface does not cool because cold particles strike it. It cools because it emits photons, and those photons leave without returning. A surface does not warm because hot particles surround it. It warms because it absorbs radiation, or because heat is conducted into it from warmer parts of the same object. This is why a shaded object can be cold while another, nearby surface is very hot in direct sunlight. The difference is line of sight to the sun, not distance through space. In the inner solar system, the sun's presence is unmistakable, and sunlight dominates whatever it touches. Yet the same region continues to show why space is described as cold. Darkness is still the default direction, and radiation still escapes easily into that darkness. Without an atmosphere to hold heat and without a dense medium to share energy, warmth remains attached to illuminated matter, while the surrounding emptiness stays a vast sink for infrared energy. Closer to the Sun, the solar system enters a region where the space is filled with streaming plasma and intense light. The Sun's gravity and magnetic field dominate, and the solar wind is young enough that its structure is still changing rapidly with distance. The environment feels more active, yet the basic reason space stays cold remains unchanged. Warmth depends on energy being absorbed and held. In near-Sun space, energy is abundant, but the material that could hold it is still sparse, and the main pathway of exchange is still radiation. The solar wind here is denser than it is near Earth, because it has had less distance to spread out. It carries electrons, protons, and a smaller number of heavier ions. The wind is a plasma, meaning the particles are electrically charged and respond strongly to electric and magnetic fields. Collisions that would normally bring a gas to a single shared temperature become uncommon, and different particles can keep different temperature values for long stretches of time. Temperature still describes random motion, but the plasma does not behave like a warm fluid that readily shares heat. As the wind expands, both its density and its internal energy thin out. The outward flow spreads over larger and larger areas, so the number of particles in a given volume drops quickly with distance. The wind also carries embedded magnetic structure, so patches of faster flow and slower flow can pass a spacecraft as distinct streams. Even in the denser patches, the material remains extremely tenuous compared with any atmosphere. Even when particles are hot in the sense of fast random motion, the ability of the solar wind to heat a solid surface by contact is limited. Heating by contact requires many impacts each second, and near-Sun space still does not provide the particle counts that air provides. A spacecraft near the Sun receives particle strikes that can charge surfaces and erode materials, but the total thermal power carried by those impacts is small compared with the power delivered by sunlight. The Sun's light arrives as a concentrated flood of photons. The particle stream arrives as a thin spray. The particles can be energetic, yet they are too few to act as a surrounding bath of warmth. This difference becomes clearer when energy per particle is separated from energy per volume. A single proton in the solar wind can carry substantial kinetic energy, and a distribution of many such protons can correspond to a temperature of hundreds of thousands to millions of kelvins. Yet the number of particles in a cubic meter remains tiny, compared with the number of molecules in a cubic meter of air. The total thermal energy stored in that volume can therefore be modest. A hot but rarefied gas contains less heat content than a cooler but dense gas. Near the Sun, space holds hot particles, but not much material. The scarcity of collisions also means that heat does not flow through the plasma in the familiar way. In dense gases, conduction is the transfer of energy by frequent collisions. In the solar wind, collisions are so rare that particles can travel long distances before their directions and energies are fully randomized. This long travel distance between effective collisions is called the mean free path. Energy can still move through the plasma, guided by magnetic fields and carried by fast electrons, but it does not create a stable ambient temperature that a solid body easily shares. The plasma remains a moving stream rather than a stationary reservoir. A surface in near-Sun space therefore lives at the intersection of two different environments. One is radiative, dominated by sunlight. The other is particle and magnetic, dominated by the solar wind. The radiative environment usually sets temperature for most materials, because absorption and emission of radiation are the largest terms in the heat budget. The particle environment shapes electrical charging and the hazards of energetic particles, and it adds only a smaller contribution to heating. The distinction becomes clearest in shadow. If a surface is shielded from the sun's direct light, it can cool quickly by emitting infrared radiation into a sky that returns little energy. The nearby hot plasma does not stop that cooling, because it cannot deliver enough heat by collisions to balance the radiative loss. Engineering near the sun therefore focuses on controlling radiation. Surfaces that face the sun must reflect or block as much sunlight as possible, while surfaces that reject internal heat must face darkness to radiate efficiently. A shield can keep sunlight off a spacecraft body, allowing instruments behind it to remain cool even while the front of the shield becomes extremely hot. The nearby plasma does not replace the missing sunlight on the shaded side, so the shaded side continues to behave as if it is exposed to a cold sky. Near-sun space also shows how quickly sunlight can heat, and how quickly darkness can cool. A surface that faces the sun absorbs power that rises sharply as distance decreases, and its temperature climbs until infrared emission balances the absorbed energy. A surface turned away from the sun, or hidden behind a shield, can radiate its heat away with little incoming replacement. In the same volume of space, one side of an object can be extremely hot, and another can remain far cooler. The vacuum between them does not moderate this difference. Only conduction through the object can share heat from the hot side to the cold side, and that conduction depends on the object's materials and structure. In this region, the idea of a surrounding temperature becomes less useful. A thermometer works by coming to equilibrium with the medium around it through contact. In near-sun space, there is no dense medium to equalize with. A temperature stated for the solar wind describes particle motion, not a background warmth that fills the region. A temperature stated for a spacecraft surface describes its radiative balance, not the plasma's temperature. Both are real, but they refer to different carriers of energy. Near-sun space is therefore a place where cold and heat coexist with little blending. The sun supplies immense energy, but it does so mainly as light that warms only what it strikes. The solar wind carries hot particles, but it does so in a thin stream that cannot easily warm by contact. Radiation remains the dominant way solid objects gain and lose heat, and the surrounding emptiness stays an efficient sink for infrared emission, even while the sun's neighborhood is filled with fast ions and stretched magnetic fields. Above the sun's visible surface, the corona extends outward as a vast, faint atmosphere. It is not a smooth shell. It is structured by magnetic fields into streamers, holes, loops, and plumes. In ordinary light it is hard to see because it is much dimmer than the surface below. Yet during total solar eclipses it appears as a pale halo stretching far into space. Instruments that detect extreme ultraviolet and X-rays reveal it more directly, because the corona shines strongly at those wavelengths. The brightness in those bands signals an environment of very high particle temperatures, even while the corona remains so tenuous that it cannot feel like warmth in the familiar sense. The corona is made of plasma, meaning gas in which electrons are not bound to atoms. In this state, charged particles respond to magnetic fields, and their motions and energies are shaped by those fields as much as by collisions. The corona's temperature is commonly described as reaching 1 million to several million kelvins, with the regions hotter still. Such numbers suggest an intense heat, and in terms of particle speeds they are. Yet the corona's density is extremely low compared with any atmosphere on Earth. It grows lower with height, and even near the base it is thin enough that particle collisions are far less frequent than in air. This combination produces a useful contrast. Temperature describes the average random motion of particles. If particles move rapidly, the temperature is high. Heat content, however, depends not only on how energetic each particle is, but also on how many particles exist in a given volume. In the corona, each particle can carry a great deal of kinetic energy, yet the number of particles per cubic meter is small. The total thermal energy stored in a large volume can therefore be modest compared with a much cooler but denser gas. A hot corona does not automatically create a warm surrounding bath for any object that passes through it, because there are too few particles to deliver energy by contact at a significant rate. The rarity of collisions also changes how energy is shared within the corona itself. In dense gases, collisions rapidly bring electrons and ions to a common temperature. In the corona, electrons and ions can have different temperatures, and the distribution of particle speeds can depart from simple thermal patterns. The corona can also show temperature differences along and across magnetic field lines, because charged particles spiral around field lines and move more easily along them than across them. The result is an atmosphere where temperature is real and measurable, yet its meaning is tied to plasma physics rather than to the behavior of thick air. The corona's structure reveals the role of magnetism. Magnetic loops rise from the sun's surface and arc back down, forming bright coronal loops in extreme ultraviolet and X-ray images. These loops are filled with plasma guided and confined by magnetic fields. Regions called coronal holes appear darker in certain wavelengths and are associated with open magnetic field lines that allow plasma to stream outward more freely. Streamers form large-scale features that extend outward and shape the appearance of the corona during eclipses. These structures show that the corona is not simply heated from below and then left to cool. It is an active environment in which energy is injected, transported, and lost while magnetic geometry sets pathways. A central fact about the corona is that it is much hotter than the sun's visible surface. This is the core of the coronal heating problem, a long-standing challenge in solar physics. Observations indicate that energy must be supplied to the corona to maintain such high temperatures. Because the corona radiates energy away and also loses energy as plasma flows outward to become the solar wind. The broad source of that energy is the sun's magnetic field, which is continually stressed by motions in the dense layers below. The precise mechanisms by which magnetic energy becomes heat remain an active area of research. Two classes of processes are often considered. One involves waves. Magnetic fields in plasma can support waves that carry energy upward. These waves can be generated by the churning motion of the sun's surface layers, then travel along magnetic structures into the corona. If the wave energy is dissipated, meaning converted into random particle motion, it can heat the plasma. Another class involves reconnection, in which magnetic field lines change their connections and release stored magnetic energy. Reconnection can occur in small events and in larger eruptions, converting magnetic energy into heat, flows, and energetic particles. Observations support contributions from both wave-related heating and reconnection-related heating. It remains uncertain which processes dominate in different coronal structures and at different times, and it remains uncertain how the heating is distributed between electrons and ions in the thinnest regions. The corona loses energy in several ways. It radiates strongly in extreme ultraviolet and X-rays through emission from highly ionized atoms. These ions emit at specific wavelengths when electrons collide with them and excite higher energy states, followed by radiation as they return to lower states. The corona also conducts heat along magnetic field lines. Conduction is the transfer of energy through particle motion and collisions. In the corona, conduction is unusually effective along field lines because electrons can travel long distances in that direction. This can move energy from hotter regions to cooler ones, especially from hot loops down toward denser layers below, where radiation is more efficient. Across field lines, conduction is much weaker, so sharp temperature contrast can persist between neighboring structures. The outward flow of the solar wind is another energy pathway. Plasma escaping along open magnetic fields carries thermal energy away. It also carries energy in the form of bulk flow. As plasma expands outward, it cools in a broad sense through expansion, while waves and turbulence can also exchange energy with particles. The corona is therefore not only a hot atmosphere sitting above the Sun, it is a source region for an outflow, and it must continuously balance energy supply against radiative loss, conductive transport, and the energy carried outward by escaping plasma. Despite the corona's high particle temperatures, its ability to heat nearby objects by contact remains limited. A solid surface immersed in coronal plasma receives impact from ions and electrons, but the impact rate is constrained by low density. At the same time, the surface emits infrared radiation. If the surface is not absorbing strong sunlight, it can still cool efficiently, because the surrounding plasma does not deliver enough heat by collisions to offset radiative loss. In sunlight, the surface temperature is dominated by absorbed radiation, not by the coronal plasma temperature. In shadow, radiative cooling dominates even more strongly. The corona is hot in the measure of particle motion, yet it is thin in the measure that determines how strongly it can warm by contact. The corona also highlights the difference between what is bright and what is dense. It can appear intense in X-rays because high-temperature plasma radiates in that band, but the total brightness does not imply a thick reservoir of heat. X-ray emission often traces where the plasma is hottest, and where density is locally higher along magnetic structures. Yet even those denser parts remain extremely rarefied compared with any atmospheric pressure at a planet's surface. A coronal loop can be a prominent feature in an image while still being made of matter so thin that it would not conduct heat like a warm gas in ordinary life. In the corona, cold and heat coexist as complementary ideas. The particles can be extremely energetic, and the magnetic field can store and release energy that keeps the plasma hot. At the same time, the environment is so sparse that heat does not behave like a blanket. Energy must be actively supplied and constantly escapes, mostly by radiation and by flow. The corona remains a place where high temperature does not guarantee warmth, because there is not enough matter to hold that temperature as a thick, shared state. It is a luminous, structured atmosphere, hot in its particle motion, and still governed by the same basic rule that makes space-cold radiation leaves easily, and thinness prevents heat from being shared in bulk. From the corona, attention moves inward to the thin boundary where most of the sun's outward energy leaves. This boundary is the photosphere, the visible surface that defines the sun's disk in the sky. It is not a solid ground. It is a layer of glowing gas where the sun changes from being opaque to being transparent. Below it, light is trapped by constant interactions with matter. Above it, light travels freely into space. The photosphere is therefore the sun's main radiator, the place where heat from deep within becomes the steady flood of sunlight that crosses the solar system. The photosphere is thin compared with the sun size. Its thickness is on the order of a few hundred kilometers, a small skin on a sphere more than 1,000,000 kilometers across. Yet within that thin layer, conditions change quickly. Deeper down, gas is dense enough that photons do not travel far before being absorbed or scattered, so energy performs a slow random walk outward. Higher up, density drops. The average distance between interactions grows, and photons can escape. That transition defines what is meant by a surface in a star. It is a surface made by transparency. Because the photosphere is where photons escape, it behaves in many ways like a glowing blackbody, an idealized emitter whose spectrum depends mainly on temperature. The Sun's photosphere has an effective temperature of about 5,700 kelvins. This does not mean every point has the same temperature. It means the overall spectrum of sunlight resembles the spectrum expected from a blackbody near that temperature. The match is close, though atoms in the photosphere absorb specific wavelengths, leaving dark lines that reveal composition and motion. Still, the main fact remains. The Sun's visible surface is the dominant source of radiant energy in the solar system. The sunlight emitted from the photosphere spreads outward through vacuum. Photons do not warm space simply by passing through it. They warm only when they are absorbed by matter, a dust grain, a planetary surface, or the skin of a spacecraft absorbs some fraction of the incoming light, turning photon energy into internal motion of atoms and electrons. That internal motion appears as heat. The warmed surface then emits infrared radiation back into space. A surface settles to a temperature where emission balances absorption, unless it has an internal heat source or an unusual geometry that changes what it can see. In this setting, contact heating is weak. There is no surrounding air to carry warmth by convection, and the sparse particles of space provide little conduction. Temperature becomes a matter of what the surface absorbs and what it can radiate away. The photosphere supplies the main incoming stream, and darkness supplies the main route outward. The strength of sunlight falls rapidly with distance because it spreads over larger spheres. At twice the distance from the Sun, the same radiant power is spread over 4 times the area. This geometric dilution is a central reason the solar system grows colder with distance. It is not because cold fills the space between orbits. It is because the Sun's photons become less concentrated as they travel outward. A surface far from the Sun receives fewer photons each second, so it absorbs less energy and its equilibrium temperature drops. Even near the Sun, the same dilution principle means that empty space does not become warm. The photosphere fills only a small part of the sky. Most directions look away from the Sun into darkness. A surface facing the Sun can absorb strong radiation and become hot. A surface turned away can lose heat by emitting infrared into a sky that returns little energy. This is why objects in space can have hot sunward sides and cold spaceward sides at the same time, even when they are close to the Sun. The photosphere is not uniform. It shows a restless texture produced by convection, with brighter, warmer patches where gas rises and darker, cooler lanes where it sinks. Magnetic fields locally alter this flow and create darker sunspots and brighter surrounding regions. The Sun is also brighter at the center of its disk than at the edge, because viewing near the edge samples higher, cooler layers before light escapes. These variations matter for solar physics, yet the overall radiative role of the photosphere remains the same. It provides a broad, persistent radiation field whose average character is set by its effective temperature. For the coldness of space, the key point is that the photosphere sets the main external heating source for almost everything in the solar system, but that heating is conditional. It depends on whether a surface faces the Sun and on what fraction of sunlight it absorbs. When a surface is shaded, the main heating term drops away. The surface still emits infrared radiation, so it cools until it reaches a new balance with whatever radiation remains. Near a planet, that remaining radiation can include reflected sunlight and infrared emission from the planet. Far from large bodies, the remaining field is weak compared with direct sunlight. Shade therefore reveals the underlying cold of the radiative environment. The photosphere can be understood as the origin of a one-way flow. Energy rising from deeper layers becomes radiation that escapes from the photosphere. Once it escapes, most of it continues outward and does not return. A small fraction is intercepted by matter, warming it, and that warmed matter emits infrared photons that also escape. The vacuum does not store these photons. It allows them to travel and disperse. Warmth must therefore be continually supplied by absorption of radiation, while cooling is always available through emission into the dark. This is why space can be described as cold even close to the sun. The photosphere radiates intensely, but it does not fill the surrounding emptiness with a shared temperature in the way a heated room does. It fills it with a directional field of photons that weakens with distance. Objects become warm when they intercept that field, and they become cold when they do not. The Sun's visible surface is therefore the surface that makes the solar system a radiative environment, where energy travels as light and where cold remains the default whenever direct illumination is removed. At the smaller scales, the coldness of space comes from the rules of heat transfer, which change when air and liquid water are absent, in vacuum. There is little matter to carry energy by collisions, so the pathways that smooth temperature on Earth fall away. What remains is radiation, the exchange of energy by light and infrared, and conduction inside solids, the redistribution of energy through direct contact within materials. Space is cold because radiation can carry energy away easily, while the return flow from the surrounding sky is weak. A piece of metal, a rock, or a spacecraft panel in vacuum is surrounded by emptiness that offers almost no particle impacts. Without frequent impacts, there is little conduction between the object and its surroundings. There is also no convection, the bulk motion of a fluid that transports heat by moving warm material and cool material around. Convection depends on a dense gas or liquid that can rise and sink. Vacuum removes that mechanism entirely. Temperature differences that would be erased by wind can persist because nothing stirs heat through the surrounding volume. Radiation becomes the main way energy enters and leaves. Radiation is not only visible light, it includes infrared, which is the form of light most warm objects emit. A warm surface emits infrared photons continuously. The hotter it is, the more power it emits, rising very steeply with temperature. This steep rise creates a strong self-correction. When a surface warms, it radiates more strongly and loses energy faster. When it cools, emission weakens and energy loss slows. A surface also absorbs radiation from what it can see. Sunlight is one part of that incoming field, arriving from a small disk. Reflected light and infrared glow from a nearby planet are another part. Arriving from a broad patch when that planet fills much of the view. Starlight in the galaxy add a faint background, and the cosmic microwave background adds a near-uniform flaw. In vacuum, what matters most is not a surrounding air temperature but the brightness of the radiation field in each direction. The surface temperature settles where incoming absorbed radiation and internal heat match outgoing emitted radiation, a state called thermal equilibrium. Two surface properties control this balance. Absorptivity is the fraction of incoming radiation that a surface absorbs rather than reflects or transmits. Emissivity is the effectiveness with which a surface emits infrared compared with an ideal blackbody, meaning an ideal absorber and emitter. Many natural materials have high emissivity in infrared, so they cool effectively when they face deep space. Polished metals can have low emissivity, so they radiate poorly and retain heat in shadow, not because space warms them, but because they cannot easily turn internal energy into escaping infrared. Absorptivity and emissivity depend on wavelength. A surface can be reflective in visible light and still emit infrared well, or it can be reflective in both. This is why thermal control uses specific coatings. A surface intended to stay cool in sunlight often reflects much of the incoming solar energy while still emitting infrared efficiently. A surface intended to retain warmth may reduce infrared emission to lower heat loss during long shadow. Geometry matters as much as materials. A surface exchanges radiation only with what it faces. A panel that looks into deep space sees a cold, radiative environment because incoming infrared from that direction is minimal. The same panel, turned to face a planet, receives a continuous infrared glow and warms. A panel facing the sun absorbs a concentrated stream and warms far more. The fraction of the sky filled by each source and the angle at which radiation strikes set the absorbed power. One side of an object can be hot and another cold at the same moment because each side is in equilibrium with a different radiative view. Inside the object, conduction tries to even out temperatures. Conduction in solids moves energy from warmer regions to cooler regions through vibrations of atoms, and in metals through mobile electrons. The way an object is built determines how strongly one surface is thermally tied to another. Thick insulation reduces conduction and allows stronger contrast between parts. Strong conductive paths spread heat and reduce extremes. In vacuum, conduction within the object is the main way heat moves from sunlit components to shaded radiators, because the surrounding emptiness cannot do that job. This interplay explains why vacuum can lead to both freezing and overheating. A shaded object with little internal heat and a clear view to deep space emits infrared and cools rapidly, because there is little incoming radiation to replace the loss. The same object in strong sunlight can overheat if it absorbs more energy than it can emit, because there is no air to carry excess heat away. The only escape route is radiation, and if emission is limited by low emissivity or inadequate radiator area, temperature rises until emission catches up. Space does not supply a stable background temperature. It supplies a dark sink that accepts radiation, and it supplies bright sources that heat only what they illuminate. The idea of a temperature of the surrounding vacuum becomes meaningful only when tied to radiation. A radiation field can be described by an equivalent temperature if its spectrum resembles a blackbody spectrum. The cosmic microwave background provides such a field, near 2.7 kelvins, and it sets a faint baseline when other sources are absent, near the sun and planets. However, the radiation field is not uniform and not described by a single number. It is directional and changing. The practical temperature of an object is therefore an outcome of exposure and design rather than an ambient property of the space around it. The inner logic remains simple. Heat stays with matter, and vacuum contains very little matter. Heat moves inside solids by conduction and across empty space by radiation, but it does not move through vacuum by convection, and it does not linger in the surrounding volume. When light is absent, objects cool by emitting infrared into darkness. When light is present, objects warm by absorbing it. Space remains cold even near the sun because darkness covers most directions, and because the emptiness between surfaces does not hold heat, but lets it escape. The wind-down begins with the simplest picture. A warm surface floats in darkness and gives off infrared light. Each photon that leaves is a small packet of energy no longer held in the surface. In air, much of that energy would be shared with surrounding molecules and might return through collisions and currents. In space, it travels outward and thins into the immense volume. The surface cools until a balance is found between what arrives as radiation and what departs as radiation. Near the sun, it is easy to imagine heat spilling into space as if emptiness could fill up with warmth. Instead, the sun supplies light, not warm air. Light is powerful where it strikes, and it is absent where it does not. A shaded panel near the sun still faces a sky that returns little energy, so it continues to cool. A sunlit panel can become hot because it absorbs a concentrated beam, while the space around it remains unable to store or spread that heat. Across the solar system and beyond, the same principle repeats. Thin gas can be hot in particle motion, yet too rarefied to warm by touch. Dense clouds can be cold because dust blocks the heating light while allowing energy to leak away. Planets and moons carry their own warmth in bulk matter and in atmospheres, but that warmth stays local and fades quickly with distance. The background glow of the universe provides a quiet flaw, but it is faint, and it does not erase the influence of shadow and geometry. In the end, cold in space is not a special substance. It is the steady result of how energy moves when there is almost nothing to hold it. Light warms what it meets. Darkness lets warmth leave. Between the two, a silent balance forms, and the universe keeps its broad, persistent chill.